Hi all, welcome to the lecture on lexical semantics, word sense disambiguation and word embeddings. In this lecture, I am not going into the detail of each and every algorithm works. I just want to give you insights on what is lexical semantics, word sense disambiguation and word embeddings. So what we will cover is lexical semantics, word senses, relation between senses, word sense disambiguation and word embeddings. So, what is lexical semantics? Lexical semantics is a study of words' meanings and the relationships between words. It asks what does a word mean and how does the meaning relate to each other words in the language. A classical example is apple can refer to a fruit or to a technology company. So, understanding which meaning is intended and why is a core challenge in lexical semantics addresses. So if you say apple, it can refer either a fruit or a company. So how far the particular machine is going to understand what is the meaning of that particular word in that context. So for that lexical semantics is used. So why this matters? Because it is a foundational concept for NLP, mainly used in machine correctly translating words requires knowing which meaning applies in context. Chatbots, conversational agents must interpret user intent accurately to respond correctly. Matching queries to relevant documents depends on understanding word meaning. So in search engines also it is very much used. So word senses means one word, many meanings. A single word can carry multiple distinct meanings depending on context. This is called polysemy or homonymy, and it is one of the central challenges of NLP. Already I have explained in my previous lecture regarding the word bank. So example bank is financial institution. I deposited money at the bank. River bank, we sat by the bank of the river. Aircraft banking, the plane banked sharply to the left. So the word bank can be interpreted as a financial institution, river bank, or aircraft banking. So which context a particular word comes. So the machine cannot determine which sense of bank is intended. This is the core problem that word sense disambiguation aims to solve. So, how words relate to each other? The lexical identifies several key relationships between word senses that structure our vocabulary. Synonymy, words with the same or similar meaning. Sometimes we refer as big, sometimes we refer as large. So, both the words may have a similar meaning. Anatomy, the opposite meanings, hot and cold. Hyponymy, a word is a subtype of another. So animal, if you say animal can be either dog, cat, horse, whatever. So animal, if you refer, you cannot specifically say this animal. Similarly, if you say color, color can be either red, blue, gray. So that is hyponymy. Meronymy means a part of whole relationship. So if you say wheel, it may belongs to the car, it may belongs to a van, it may belongs to a and then car, if you say, it may belongs to a vehicle part, so vehicle becomes car. So hyponymy and mononymy has a little bit relationship with each other. So the main difference between polysemy and homonymy is one word, multiple related meanings. If you say one word and multiple related meanings, so if you say foot, it's a body part, foot of a mountain, foot of a page. Okay, so it is related meanings. But homonymy is one word, multiple unrelated meanings. For example, if you take bat, bat is a flying mammal, a cricket or a baseball bat. So it is both are different contexts here. But foot means at least one thing which is common is it is at the down, as a body part which is at the down, foot of the mountain, foot of the page. So that is what. So both polysemy and homonymy involve in a single word form with multiple meanings. The key distinction is whether those meanings are related or unrelated. If it is related, it becomes polysemy. If it is unrelated, it becomes homonymy. So we will go into word sense disambiguation. WSD is the task of determining which meaning of the word is intended in a given context. It's a fundamental step in making NLP systems truly understanding language rather than just processing it. So four approaches you can go with: supervised learning, unsupervised, knowledge based, and hybrid. Supervised means you can use labeled training data where the correct sense is annotated, high accuracy but requires large data sets. Clusters word usages without labeled data, more flexible but generally less precise. Knowledge based relies on lexical resources like WordNet to match context to sense definitions. Combines multiple approaches to leverage the strengths of each method is hybrid. So any one of the approaches you can go based on the applications you are going to use, based on how much data set you have, all that matters, so that you can choose any one of the approaches in WSD. One concept is there in WSD is word embeddings, which is very important in the topic of NLP. Word embeddings are dense vector representation of words. Each word is mapped to a point in a high dimensional mathematical space. Words with similar meanings are placed close together in that space. This allows machines to capture semantic relationships mathematically, enabling powerful downstream tasks. So, as if you say clustering or something, when you put the words, highly similar words are placed close together in that space. So, you take a high dimensional mathematical space, and then in that, if it is close together, that has a similar meaning. So where we will use word embeddings is text classification, sentiment analysis, and machine translation. So text classification is you can categorize documents, emails, or reviews. Sentiment analysis is detecting positive, negative, or neural tone in text data. Machine translation is mapping meaning across languages using shared vector spaces. Now we'll see word to vec. In word to vec, we will see the neural embeddings that learn the meaning. Word2Vec is a neural embedding model introduced by Thomas Miklov in 2013 at Google. What it does is it learns the semantic vector representation of words by training on the large text corpus. So the model captures meaning so precisely that vector arithmetic reflects real world relationships. So famous example, whenever you open Word2Vec, if you search, there is an example like king minus man plus woman, it will be approximately equal to a queen. So this equation demonstrates that Word2Vec encodes semantic analogies as uh, geometric relationships in vector space. So a king minus a man means he's not a man, plus a woman, that means mostly it will be a queen. So this type of understanding, which takes a semantic analogies in a geometric relationships in a vector space, is called as a Word2Vec. So how Word2Vec works is it takes the input corpus. Input corpus is nothing but your input text large data set, okay, and then it will do the neural training and it converts to the Word2Vec, word as vectors. So Word2Vec trains a shallow neural network on a large corpus. The network learns to predict words from their neighbors, and the internal weights become the word vectors. So it encodes the meaning through usage of patterns. So Word2Vec actually is helpful for a large corpus, means large text of data or large documents, or the input data is more. Okay, so the network learns to predict from their neighbors and the internal weights. So it introduces the neural network concepts, and then it finds out how the usage of pattern is there in that particular words. Then this Word2Vec uses two different types of methods in which it can find. One is called as CBOW, which is continuous bag of words. So how it works is CBOW predicts the target word using the surrounding context words. The model takes multiple context words as inputs and outputs, the most likely word to fill the gap. Okay, so it takes all the multiple context words and then most likely will fill the gap. So she is a dash dancer. If you put she is a great dancer, beautiful dancer, like that, you can fix a particular word. But whichever is filling the gap exactly proper based on the sentences, that will be taken. So that is how this particular continuous bag of words works. So it predicts the target word. So the target word here is she is what type of dancer, that is the target word. So key strengths is it is faster to train than skipgram. We will see skipgram because word2vec can use either cbow or skipgram. Okay, so but cbow is faster than that, more efficient for frequent words, averages context signals for smoother prediction. It is well suited for large general purpose corpus. So for that it is mainly used. So this is skipgram model and this is cbow model. Both actually use both definitions are almost same. It wants to find the target word. Okay, so but how cbow works and how skipgram works we can see through this. So context works surrounding the blank. You can see how it is fed here all the words and then it trains and then it gets the particular target word. Okay, here what happens is you will get the target word as the input, it goes into the model and then it gets the surrounding context words. So it what happens is if you give one word and if you search for that word in the particular context, this may have a slower training, but there from the training you are going to search for the target word, that will have a faster training. So this is better for cbow is better because it is having faster training and better for frequent words. Skipgram is slower training and better for rare words and for smaller data sets. So both architectures are the part of word to neck framework. The choice depends on the data size and the word frequency distribution. So if the data size is smaller and the frequency is rare, then they go with skipgram. If the data size is bigger and it is the words are frequent, then it goes to cbow model. So word2vec uses both cbow and skipgram based on the choices depending upon the data size and the word frequency distribution. So cbow architecture, context words, embedding layer, average hidden and target word is the architecture layers. The cbow averages the embeddings of all context words before predicting the target. This averaging makes it robust and fast, but it loses some positional information compared to scriptgram. Skipgram predicting the context from target. Unlike cbow, skipgram takes a single target word as input and tries to predict the surrounding context words. This makes it especially powerful for rare words as it generates more training examples per word. So better for rare words, slower but more precise. Skipgram is slower but more precise. So training is slower than cbow, but representations tend to be richer for low frequency vocabulary. So this is the same thing which I have shown there. This is again a little bit in depth how word2vec chooses the particular model, cbow or skipgram. So one hot encoding if you use for individual features here, then the hidden layer can be of window size 3, predicted one hot vector of target feature. So for each node, we predict three values due to the window size is 3 and actual target is the value given there. But here you fed the in skipgram, you fed the actual target as the encoding and then three nodes in hidden layer, window size is 3, predicted vector of independent feature 1, predicted vector of independent feature and then actual target. So based on this, the script you can analyze how it works in the neural network. So putting all together is first we saw lexical semantics, So it studies words, meanings, and relationships between words. And word senses, if one word can carry multiple distinct meanings, then that is word senses. And we saw WST, which resolves ambiguity by determining the correct sense from the context. Then word embeddings, which represent words as dense vectors in semantic space. Then we saw about word to vec algorithm, where it uses either CBOW or skipgram. So it is a neural model that learn embeddings from large corpus. That is what we have seen. And then this is the key takeaway. Meaning is complex. Words carry multiple senses. So the meaning is complex. Context is a key. So the WST uses surrounding words to select the correct sense automatically. Vectors encode meaning. So word embeddings capture semantic relationships as geometric distances. Word to vec learns either CBOW and skipgram learn rich representation from raw text data. So thank you. So these are the topics which we have covered here. The detailed explanation of each and every algorithm will be there in the later lectures. Thank you.